what do you want to prove? So you want to prove if two conditions hold. Okay, if n equals to m, then Pn is true. And the second condition is if for n equals to n0, Pn is true. Then for n equals to n0 plus 1, Pn is true. If you have these two conditions, then you can claim for all n greater than or equal to m, the statement Pn is true. Okay, so let's look at the proof. Again, we are use the abstract property for natural numbers. We'll first define a subset of the natural numbers. So we'll let S be the set of all natural numbers. K in N such that Pk is not true. So S is a set of natural numbers K for which the statement P is not true. All right, there will be two cases. So case one, that is S is empty. In other words, the first case is S contains no element. Then what does this mean? If S is empty, then that means no natural numbers, so that P of K is not true. In other words, every natural number K, the statement is true. Okay, I should say this. K in M, and I should add one more condition here, and K greater than or equal to M. Okay, in this restriction. So if S is empty, then for no K greater than or equal to 2 equal to M, then for no K greater than or equal to M, Pk is not true. So that is for all K greater than or equal to M, Pk is true. All right, so this is a very simple logic in the first case. The first case, if the set S is empty, then we're done. We're done, okay? So this is a trivial case. So the second case is S is contains at least one element. Okay, if S contains at least one element, then that means S is a long-empty subset of the natural numbers. So S is a long-empty subset of the natural numbers. So if you remember the abstract property for non-empty subset of natural numbers, it must contain a minimum. Hence, S has a minimum. Say M0, okay? All right, so what we know is that this M0 is not M because we have two conditions which satisfies. Because the first condition is if n equals to m, then Pn is true. So this is our first condition. So that means M0, okay, since, let me go to the next page. Okay, since for n equals to mm, Pn is true. So we know M0 is not equal to m. All right. The reason is M0 is a member of S. But our set S is a set of all natural numbers so that Pn is not true. So M0 is not equal to M. And moreover, since M0 is greater than or equal to M, this is the definition of the set S. All members in set S are greater than or equal to M. We have M0 is strictly greater than M. Okay, M0 is not equal to M, but M0 is greater than or equal to M. So M0 is strictly greater than M. So this tells us, so M0 minus 1 is greater than or equal to M. All right, because M0 is strictly greater than M. So if you subtract a 1, it's still going to be greater than or equal to M. And we know since M0 minus 1 is less than M0, and M0 is the minimum of S. So what we conclude is that M0 minus 1 is not in S. Because M0 is already the minimum. But M0 minus 1 is less than M0. So M0 minus 1 is not in S. Okay, if M0 minus 1 is not in S, by our definition of the set S, we know that P of M0 minus 1 is true. Now, if you look at our second condition, if P of M0 minus 1 is true, then for n equals to m0 minus 1 plus 1, the statement is still true. So by our second condition, P of m0 minus 1 plus 1, which is just as P of m0, is true. But this is a contradiction. This is a contradiction. Since m0 is in S, okay, because all members in S satisfies P of n is not true, but we get a P of m0 is true, so it's contradiction. So this tells you the second case cannot happen. So remember, we have the two cases. The first case is S is empty. If S is empty, we are fine. But in the second case, if S contains at least one element, we get a contradiction, which means the second case cannot happen. So it can only happen the first case. But in the first case, we're fine. So the proof is finished. It's done. Okay, so you can also check the proof for in your notes for the standard mathematical induction. Actually, the proof is similar. All right, so do you have any questions about this proof? Okay, so you can ask any other questions if you have.
Can you go over the first problem in our homework, please?
Okay, 2.7. Okay, so the first one is we want to show n factorial is greater than or equal to m plus 200. So the second one is m factorial is greater than or equal to 2 to the n. Okay, let's first look at A. So by mathematical induction, let's check the step 1. Check the first case for n equals to 1. So we have the left side is equal to 1 factorial, which is equal to 1. And the right side is equal to 1. Oh, I think this is there's something we need to figure out for the first one, because the first one is just for n not large enough. So we have to figure out the first one. So n large.
N large enough should be 6 for that one.
Large. You said what, 6? Let me see. 6 is that is 6 big enough? I think 5, 1, 2. Yeah, 6. Okay. So the starting point is 6. So the step 1 is for n equals to 6. So the left side is equal to 6 factorial is 720. And the right side is equal to 6 plus 200 is 206. So we get the left side is greater than the right side. Okay, so this is the step 1. So step 2, so assume for n equals to n0, we have n0 factorial is greater than or equal to n0 plus 200. Okay, so for n equals to n0 plus 1, let's compute first the left side. So the left side is equal to n0 plus 1 factorial. So n0 plus 1 factorial, by definition, this is n0 plus 1 times n0 factorial. Okay, this is a definition of factorial, n0 factorial. Okay, now we can use our assumption. Since n0 factorial is greater than or equal to n0 plus 200, so the whole thing would be greater than or equal to n0 plus 1 multiply n0 plus 200. Okay. Okay, so in this quantity, since n0 is a natural number, so the first part, n0 plus 1, would be greater than or equal to 2, because n0 is greater than or equal to 1. So this is greater than or equal to 2 times n0 plus 200. Okay, so this is, if we write it, this is n0 plus 200 plus n0 plus 200, because this is 2 times n0 plus 200. So you have 2 of those. But each parenthesis is greater than or equal to 1. So this is greater than or equal to n0 plus 200 plus 1, because one parenthesis is greater than or equal to 1. All right? So this is exactly equal to the right side. Okay? Because the right side, when n equals to n0 plus 1, that is n0 plus 1 plus 200. That's exactly this. Okay? So are you fine with A?
Yeah, so if you could just leave it up for just one more moment, though, please.
Okay.
Okay, thank you.
Let's go to B. That is n factorial is greater than or equal to 2 to the n. So B, let me write n factorial is greater than or equal to 2 to the n, again for n large. So what is the initial value for this one? Is 2, 3?
It's 4.
4?
Yes.
4, okay. So step 1. So for n equals to 4, so you have the left side is equal to 4 factorial is equal to 24. And the right side is equal to 2 to the 4 is equal to 16. So you have the left side is greater than the right side. Okay. Initial step is fine. And step 2, assume for n equals to n0, we have n0 factorial is greater than or equal to 2 to the n0. Okay, so for n equals to n0 plus 1, so the left side is equal to n0 plus 1 factorial. By definition, this is n0 plus 1 times n0 factorial. Okay, again, here we have an n0 factorial. By our assumption, we have n0 factorial is greater than or equal to 2 to the n0. So this is going to be greater than or equal to n0 plus 1 times 2 to the n0. Now, by the similar argument, since n0 is a natural number, in particular, n0 would be greater than or equal to 1. So n0 plus 1 is greater than or equal to 2. So this is going to be greater than or equal to 2 times 2 to the n0. So this is exactly equal to 2 to the n0 plus 1, which is equal to the right side. Okay, so actually the B is even easier when you use this estimate. Okay, so we are done.
I'm sorry, could you explain one more time why n0 plus 1 turned into 2?
Okay, so here is the n0 is greater than or equal to 1, right? Because n0 is a natural number. Correct? Yeah, okay. So n0 plus 1 is greater than or equal to 2, right? I think from this step, here we use the assumption. Okay, n0 factorial is greater than or equal to 2 to the n0. But from here to here, this part, we just use n0 as a natural number. We don't use anything else. Yes, yes. Okay. Any other question? Okay, so if you don't have any questions, then you can leave now. So otherwise, you can ask me. Okay.
Have a good day. I appreciate your help.
Yeah, no problem.